So let's look at it here. Now, the rates of decomposition of hydrogen peroxide can be investigated by withdrawing fixed volume of small samples of the solution at fixed time intervals into a conical flask containing co-dilute sulfuric acid and titrating the resulting mixture with a standard potassium manganate solution. The following results are shown in the table given to you. Then the question asks us to show that the decomposition is first order with respect to hydrogen peroxide, and then determine the rate constant. So there are two jobs that we need to do in this question. Okay, so let's look at what is sampling method in general first. Either we have known reactant that we mix together and we start T equals to 0. We need to maintain the temperature. But in this case, because it's decomposition of hydrogen peroxide, so basically I just need to have known concentration of hydrogen peroxide and I start timing it. Okay. And then at regular time interval, I will draw a sample of a fixed volume out and I will quench it, meaning I will slow it down so much that it's almost stop at that moment of time that I draw it out. And then I keep this sample at the side at time equals to 0, time, okay, not so much of time equals to 0, but time equals to 4 minutes, time equals to 8 minutes, time equals to, So then we have these samples done, and then we will perform a titration to determine the concentration of either the reactant or the product in the reaction mixture at time t, so that we can plot the either reactant or product time graph. So this is the general idea of how sampling is done. So let's come back to our example here. Let's read the question. They say decomposition of hydrogen peroxide. So we need to know that hydrogen peroxide will give you oxygen and water. Okay, this is my equation. Sampling method is a continuous method and experimental result allow concentration time graph to be plotted. By concentration of who is the problem now, right? So you can easily guess because you're titrating with KMnO4, your oxygen and water is unlikely to be the candidate. Seems like it is reacting with my leftover H2O2. So I'm actually getting a concentration of reactant left time graph. Why samples are pipetted into co-dilute sulfuric acid in the question? Now, we obviously is trying to do this action of quenching. So cold solution will quench the reaction by slowing down the rate of reaction, and H2SO4 also provide the H plus for redox titration later on with KMnO4. So that is like a very careful choice of uh, reagent at this point. Okay, so please note down all this information. During the titration, what is being titrated with KMnO4? I just happened to talk about it earlier. So the H2O2 left in the sample at the time of sampling is what we are having. So if we were to plot the volume of KMnO4 used against time, we are essentially having a concentration of reactant time graph being represented. So they say show that decomposition of hydrogen peroxide is first order reaction and then determine the rate constant, right? So let's focus on how do we show it is a first order reaction. We are having a concentration of reactant time graph. So in order for us to show first order reaction, we are going to find half-life. On a concentration reactant time graph, we find successive half-life, and if half-life is constant, that's how you can prove that it is first order reaction. So I think that's why we need to think through looking at the question, what should we do with it? So do we need to calculate the concentration of H2O2 from the volume of KMnO4 for every sample so that you can plot? Actually, we don't have to, because the number of mole of H2O2 left is directly proportional to the number of mole of KMnO4 used to titrate against it. So then that means the concentration is directly proportional to this. The concentration of KMnO4 in the volume of sample is never changing, and therefore the volume of KMnO4 used is representative of the concentration of H2O2. I'm going through this explanation so that you know why we can use the concentration, the volume KMnO4 time graph to to in place of the concentration of H2O2 time graph. So there's no need for us to calculate concentration of H2O2 left for each sample. We can simply use the volume of KMnO4 graph against time to find successive half-life. So this is the part of the reasoning that I really need you guys to appreciate to journey on in this reaction kinetics study. So the graph, if you plot, will look beautiful like this. This is very clearly a reactant time graph. And so we will then have to look for our half-life, second half-life. Take note, this is actually quite unfortunate, quite a regular mistake that students and your seniors have made. The half-life is the time taken for it to be half. So take note of the green part where my second half-life is. It doesn't start measuring from 0. It is actually measured for the duration for it to drop to that half. Okay, so please take note. Note how I actually label the two half-life because I would needed to differentiate the first and the second half-life. So I use a bracket and a subscript. Okay. So from the graph, we can tell that first half-life is equals to second half-life equals to 12 minutes. And so since the successive T-half is constant, we can say that it is a first order reaction. The question asks us to prove, and we prove it this way. Take a moment to take note of the various things that I need you to label. The labeling technique needs to be there. So you need to label that particular range and label it as the T-half. And the half-life is not that point, but rather that range of duration of 12 minutes. The question also asks you to find rate constant, right? So T half equals to log 2 over K. And it is already told to you in the question that it is a first order with respect to H2O2. You only have H2O2 as the reactant. So the reaction is overall first order as well. You can use this equation because of that. So here we go. Take note of my unit of K. It is actually minute minus 1, and the minute was from the graph. The graph has time in terms of minute.